G'day, here's just another couple of videos on some circle theorems and this time we're going to be looking at tangents, things that come inside the circle. I just need to clarify what a tangent is and I guess the point of contact as well, and a few things. A tangent is something that, a line that just touches the circle once and only once. So unlike a chord which chops through 2 points, the tangent only touches at one particular point. I'm going to say that it touches at this point T. Okay, so that's the tangent. The point of contact is where it touches at T, and the length of the tangent is simply the length from P to T. Okay, just things that you need to know for this topic. Now, the other thing the other theorem that you can probably see down here, that the tangent is perpendicular to the radius. The reason that that is true, well, this is the way that I think of it anyway, is that if I imagine trying to get from the center of the circle to this line, the shortest way to go there is not to go over here somewhere, but the shortest way is to actually go there, which is the radius. The absolute shortest way to get from this point to this line will be when that is a right angle there. So therefore we can say that this line here is perpendicular to this line here. So whenever that you've got a tangent, there is always a line, the tangent is always perpendicular to the radius. Okay, a line to the radius. Now this is one of the things that we covered in the last topic. It would have been probably helpful to know that then, but we probably know that now, so that's good. Okay, I'll go through the next one. The next one is Theorem 6, again looking at tangents. Imagine this time that we've actually got two tangents from the same point. So this point P over here has a tangent up there, and it also has a tangent down here. What am I going to call that? I'm going to call that Q, just for the sake of it. Okay. Now, a couple of things that we know from this is that we know that there's a right angle, a perpendicular line going from the point T down to the center, and also from there as well. So these things here are right angles. We also know that this length is the same as this length here, because it's simply the radius. We also know that this line here, this dotted line, is the same for both triangles. If you imagine this, this line here sort of goes directly from P to O. Now we've got two triangles, one there and one there. That line there is going to be the same for both for both triangles. Therefore, that means that this, because we've got two sides that are the same, these two are the same and these two are the same, that means that these two over here will also be the same as well. And so that gives us the Theorem 6, which is two tangents drawn from an external point to a circle are the same length. So PT is the same length as PQ. Okay, go to Theorem 7. Theorem 7, imagine that we have a circle here with a tangent that touches at this point here. We'll call that C. Now I'm going to draw a chord from C up to this point here, D. Now I'm also going to draw a line straight up here. So that one's obviously a right angle to the point E, and then I'm going to connect the triangle here like that. Now what I'm going to do is I'm going to compare these angles in here with this angle up here. So I'm going to call this angle X, the angle that makes CD makes with CB, and I'll call this angle in here Y, and I'll call that angle up there Z. Okay. Now I need to make a couple of assumptions about this. I guess, this is not necessarily an assumption, but I need to know that X plus Y must equal 90 degrees. Okay. The other thing that I need to know, or make reference to something in the past, is that from Theorem 3, you'll remember that if there's a straight line here that goes through the center of the circle, which, sorry, I should have clarified that does actually go through the center of the circle. That's the radius, that if you've got a line that goes through the center of the circle, then where it connects to the other point of the circle will also be a right angle. That's from Theorem 3, if you remember that one. Okay, now we have this triangle. We can also see that angle Z plus angle Y plus this angle here, which is 90 degrees, that is just a triangle, so that has to equal 180 degrees. So I guess we can deduce from that that z plus y must equal 90 degrees. Now, if z plus y is 90 degrees and x plus y equals 90 degrees, then we must conclude from this that x actually equals z. Okay. Now that means that the angle, that's the theorem 7 says that the angle between a tangent and a chord, here, drawn from the point of contact, so that angle in here, is equal to any angle in the alternate segment. We've got the segment here, and this is the alternate segment out there. So anytime a line, we draw a line from the point of contact to another point in the circle, it will make it will make two segments, and I guess the alternate segment, this angle in here, z, will also equal this angle here, x. Now I know I drew straight up here because I thought that was the easiest one to see, but it's actually true for any other point in this alternate segment anywhere. So if I say put this line here and I drew this triangle there, that would also be true as well, because if you remember that this angle here is the same as this angle here from, I think that might have been theorem 2, that means that this angle here is the same as this angle here, which is the same as that angle there. So anytime we get we get a chord that connects to the point of contact over here, and then makes any triangle out in the alternate segment anywhere up here, we can say that this angle here is equal to that angle in there. Okay, thanks very much. That will sort of help you with 10b, and then I'll do 10c in the next one.